The next type of function that we're going to be working with and really going in depth on are polynomial functions. We've already studied two types of polynomial functions, linear functions and quadratic functions. Linear functions, if you'll recall, are functions of the form f of x equals mx plus b, and quadratic, if I put them in standard form, would be f of x equals ax squared plus bx plus c. Okay, these are polynomials of degree 1 and degree 2, the degree being the largest power on the x, right? Degree 2 because there's an x squared, degree 1 because there's an x to the 1. Now in both of these cases, and sometimes we write the linear as, instead of mx plus b, you might see it ax plus b. That's okay as well. You'll see that on your calculator when you're doing your linear regression. Now in both of these cases, we're using letters to represent the coefficients on the variable as you go down the line. And we typically write them in descending order of the degree, again the degree being the power within the term. So here we have a degree 2 polynomial taking the largest power, but each term has its own degree. Here's degree 2, degree 1, degree 0. Degree 1, degree 0, okay? And we use these letters to represent the coefficients. Well, it could be the case that eventually, you know, if we were to add terms to this, make it cubic or a quartic polynomial, a cubic would just add a third degree, quartic would add a fourth degree, and so on. Eventually you get so many terms, you run out of letters to use, like A, B, C, right? If you get past 26 terms, or a 27 degree polynomial, we're going to run out of letters to use. So the general structure of a polynomial that we're going to use, or the general formula, instead of using A, B, C, we're going to use subscripts in all A's. So it's going to be A sub n. In this case we call it A sub 2. In the case of the quadratic it'd be A sub 2x squared plus A sub 1x plus A sub 0, rather than using A, B, C. Again, because that could be the case that you run out of letters eventually. So our general form of a polynomial has A sub n, that's your leading coefficient, times x to the n power, n being your degree. Then you subtract 1, right? So you always drop 1 as you go down. So n minus 1 is the next whole number down, times x to the n minus 1. Eventually you get down to the x squared term, the x term, and a constant term, the constant being A sub 0. Now the subscript, along with the power, they represent the degree of the term. The A sub 0 down here represents a constant, a 0 degree term. All of the powers and subscripts must be whole numbers, okay? You can't have any fractions or decimals or negatives as your powers in order to have a polynomial. You can have those things mathematically, but they're not called polynomials, they're called other things. And so polynomials must have whole number powers, whole number degrees on each term, okay? 0 through infinity. Okay, so that gives us just an idea, and that's how this, I don't know, the structure of this formula works out. You'll see that a few times throughout the course, throughout this section, so that general formula for a polynomial. Now, of course, there are some terminology. There's some terminology you probably already know and are familiar with, but I'll just kind of rehash a couple things. First of all, you have a leading coefficient. The leading coefficient is the coefficient on the largest degree term. So in this case, it'd be A sub n, whatever that is, okay? The leading term is this entire term, and the degree of the polynomial is the degree on that leading term. Okay, so those things all go together. The constant, of course, is the term that has no x on it. Okay, all of these a's with a subscript are considered coefficients, including the constant. Okay. Okay, now we've seen the graphs of linear and quadratic polynomials. We're going to generalize to others. We've also seen the graph of cubic polynomials as well, okay, when we did the library of functions. So now we're going to generalize to other degrees, and then we're going to add more terms on there to see what happens to the graphs. Okay. Couple really important features of all polynomials is that if you want to find the y-intercept, the y-intercept is a very interesting point, because if you plug in a 0 to the function, that's how you find a y-intercept, use x equals 0. Well, every term ends up being 0 except the term that doesn't have an x. And so the simplified form is just that a sub 0. So whatever that is, that's your y-intercept. Now that makes sense with both the linear and quadratic examples we've seen already, right? When you're looking at a linear polynomial, mx plus b, or you could think of it as a sub 1x plus a sub 0, that's your y-intercept. We call it b usually, but we'll call it a sub 0 as in general. That's your y-intercept. Same thing with the quadratic. You have a, b, c, the c being your a sub 0, and that's always your y-intercept. Okay? So your constant term is the only thing left when you plug in 0. So that's going to be your y-intercept. Will always be 0 comma a sub 0. Okay? All right. For x-intercepts, you always substitute 0 in for the function. Right? So for x-intercepts, you substitute 0 equals the a sub n x to the n plus dot dot dot. I'm just going to skip some of these, writing some of these terms. Right, I'm skipping a couple terms in there, but you know what I mean. You know, you set the polynomial equal to 0 and then solve for x. Now, the way that we solve this for x depends upon the size of the polynomial, or the degree of the polynomial. If it's linear, we have some very specific rules where you add or subtract the same amount to both sides, or divide the same amount. And so we can solve a linear equation very quickly. Quadratic equations require the quadratic formula. We've seen that before. Or factoring. You could also use factoring, which we haven't done a whole lot with. But we're going to be getting into factoring quite a bit now. So factoring is more general, because the quadratic formula only works for degree 2 polynomials. If we get to cubics and quartics and 27-degree polynomials, something like that, you need to be able to factor. Factor is the only way to really solve these for x, to find the x-intercepts. Okay, so typically we're going to solve by factoring. Now, they're not always factorable, but if you can get them factored, that's the way we're going to solve them. Okay. There are many other aspects of a polynomial graph that are important, but these are just a couple general principles that you can always find, or always work toward finding, using just plugging in 0 for one of the values. Okay. The other thing that's very important, we'll go through some examples later of how to do this specifically. Another thing though that's really important is to be able to really just determine the behavior of the graph, the general shape. Okay. The general shape is important. And so we're going to start out by just looking at a few examples of power functions. The power functions are just individual terms. They're monomials, or polynomials with a single term, but they could vary in degree. So you just have maybe an x cubed term, or an x to the 6th term, and you don't have anything else. Okay, all the other coefficients are 0. So a power function, if I look at, if I increase the degree on a power function, if I look at maybe x to the 1, for instance, well, we know that that's a line, right? first degree polynomial is a line. In fact, let me just go by degree rather than writing out an example. So if I have a degree 1 polynomial, we know that that's a linear graph, right? We've seen those already. One side goes up, one side goes down, assuming that our leading coefficient is positive, right? Our slope, if our slope is positive, we have this increasing graph. Remember, the slope is a sub n for a 1 degree polynomial. Your slope and your a sub n, your leading coefficient, are the same. Now, if you have degree 1 but a negative leading coefficient, your graph will go downward. Okay, so a negative slope essentially. And so you have this decreasing graph. Okay. What's going to be interesting is that when we deal with any odd power, you're going to have a similar behavior in the graph. You're going to have increasing for leading coefficients that are positive and decreasing for leading coefficients that are negative. The reasoning for that is because when you raise a positive to an odd power, you get a positive value. When you raise a negative to an odd power, you get a negative value. And so you have basically all your points are in the third and first quadrants. If you then multiply by a negative and make that leading coefficient negative, it reflects the graph across the x-axis. That's one of our transformations we've seen. And you end up with everything from the bottom going up and from the top rotating down. Okay, or reflecting down, I should say. And so you end up with this decreasing graph. Okay, changes all of the signs. Okay, so I can apply this to all odd powers because those behaviors are the same. Positives become positive, negatives become negatives whenever you raise to an odd power. So if I were to change that to a degree 3, I'm looking at odd powers now, or odd degrees, then the graphs are going to have a similar behavior. However, there's going to be more curvature to it, right? We've seen the cubic function before. And so you end up with a curved graph, but with the same sort of behavior in the tails being the arrows, right? So on one side it goes up to the right, the other side it goes down to the left. And that's for positive leading coefficients. Now if you, again, have a negative leading coefficient, that would give you your reflection across the x-axis, which then gives you a decreasing graph instead of an increasing graph. Same idea, but now it's curved. Okay, so you have this curved graph. But again, the end behavior, call it the end behavior, it's really these tails are the same. Okay, so the end behavior what we call the end behavior is really just the direction of the tails. And the end behavior, what's going to happen is the end behavior of larger polynomials will always follow the end behavior of the power function corresponding to the largest term, the leading term. Okay, we'll see that shortly. We'll get more into that, I guess. Okay, so if I were to extend this to degree 5, degree 5 polynomial, we haven't really studied degree 5s yet, okay, or anything larger, degree 7, degree 9. But what will happen is that you're raising things to a higher power, right? So if I raised 5 to, or 5, well, either way, 5 to the 5th power instead of to the 3rd, it's going to be higher up. And so your graph is going to be increasing faster. However, if you were to raise a small number, like 1/2 to the 5th power, it actually gets smaller. Okay, raising raising numbers between 0 and 1 to a higher power, make this number smaller because the denominator gets bigger. And so what you end up with is a graph that is flatter in the middle. Flatter in the middle because it's pulled down toward the x-axis. But then on the ends, it increases faster. So it becomes steeper. Okay, so it's flatter in the middle but steeper on the ends. What's interesting about all of these, and of course the end behavior is the same, right? So it's going up to the right, down to the left. Same thing here. Degree 5 is going to be flatter in the middle, steeper on the ends. Flatter in the middle, steeper on the ends. So it's a sharper bend. Okay, sharper bend. And what's going to happen is that on all of the power functions, whether they be y equal x, or y equal x cubed, or y equal x to the 5th, or any y equal x to an odd power, there are 3 points that all of them contain. First of all, they all go through the origin, right? Because 0 raised to any of these odd powers is still 0. So they all contain the origin 0, 0. On the right-hand side, of course, I'm looking at positive coefficients here, so I'm looking at the positive side. On the right, they all contain 1, 1. Okay, they all go through the same point 1, 1 because when you plug a 1 in, raise it to an odd, you get 1. So 1, 1 is always on the graph. And again, looking at the positive side, if you go, the positive leading coefficient, if you look at the negative x values, all of the graphs will go through -1 because if you raise -1 to an odd power, you get -1. Okay, so you'd have -1, -1 always on the graph as well. So these 3 points would be on the graph of every power function whose coefficient is 1. Okay. Now, if I multiply these by another coefficient like 7, if I had 7x to the 5th or 7x to the 3rd, then that would just change these outputs to -7 and +7 on those 2 points, whatever the a sub n is. Okay. But these 3 points generally don't change by adding power. So if I wanted, x to the 51st power, as long as that's an odd power, it will contain these 3 points. Okay. If I wanted -x to the 51st power, then I just change the sign on the outputs so that the negative input gives me a positive output and a positive input gives me a negative output, and I get the same thing. Okay. All right. So that's just an idea for odd, powers or odd degrees. So again, it will flatten out in the middle between -1 and 1. It flattens out because everything gets pulled closer to the x-axis. And outside of that region, greater than 1 and less than -1, everything stretches out. Okay, and then they get farther away from the x-axis there. Okay. In the next video, we'll talk about the even degrees.